Hi, Assalamualaikum. My name is Thermo Material Lab. Okay, today our group will present the report about experiment 5, bending moment. Okay, this is my group members, Abdi Majid Gili Awi, Melvinci, and me, Nazirul Hilman Mazukri, Nurul Nadra binti Zulkhairi, Hud Muhammad Wasami. Okay, for the abstract. The aim of the experiment is to determine the bending moment of material in loaded beam normal section. The experiment is carried out with an experimental beam that is separated into two parts and connected by a joint. Therefore, a frictionless hinge with a moment of resistance provided by an underspring balance. Load is induced onto the beam by placing three load hangers part of the beam. When a load is applied to the beam, it begins to bend. Every time load is changed for a new placement, the spring balance is turned to align both parts of the beam. The load's net force is then determined by reading the spring balance. The process will be repeated for different placement of load hanger on the beam with different loads in this experiment. The bending moment for each load placement is calculated using all of the data obtained through the experiment. To compare experimental and theoretical bending moment values, graph of bending moment against distance construct. The theoretical value will be applied and discussed. Finally, principle of bending moment is relevant to calculate the bending moment despite having small difference between experiment and theoretical value. The difference of value is due to error occurred in the process of conducting the experiment. And for the introduction, a bending moment is the reaction that occurs in a structural element where an external force or moment causes the element to bend. The beam is the most basic or simplest structural feature subject to bending moment. The objective of the experiment is to measure the bending moment of material. Okay, for the third part, bending moment is the torque that keeps a beam together or also can be defined as a force that causes something to bend. We can measure the bending moment by cutting the beam, then calculate the algebraic sum of the moment required of all the forces that are acting in the one side of the section at the left half side or right side to hold the beam stationary. Okay, we can simply, for the equation is force time by length. Okay, there's two sign convention. Okay, first positive bending, sagging bending on the top, compression in top fibers and tension in bottom fibers. Okay, for the negative bending, honging bending, the tension in top fiber and the compression in the bottom fiber. Next, okay, for the teori part lagi. Firstly, there is a vertical force P acting on the cantilever beam in figure A. Okay, when the load beam is cutting through at cross section SS, the shear force Q and the bending moment M are created at figure B. Okay, for A of the beam, the direction of shear force as figure B on the blue box and the direction of bending moment figure C in the red box are assumed to be positive. For part B of the beam, the positive direction is the opposite. To achieve vertical equilibrium of part A, the shear force in figure 2 blue box is equal to negative RA, whereas for part B, the shear force Q evidently acts as shown and has the value of positive. Okay, the formula is equilibrium moment for part A is Ms equal to Ra times by A, and for part B, Ms equal to Rb times by V negative P times by B minus L. That's all for my part. Thank you.
Hello, I am Hud Mohammed and I will present the methodology. We have here apparatus, we have beam supported load hanger. The load hanger we have P1, P2 and P3. We have also loads of 5 Newton, 10 Newton, 15, 20 which we will use. Furthermore, we have here spring balance, spring gauge and fixed joints. Procedure Table 1 or Part 1. The beam is set up where the load hanger B2 is from 250 mm from B1, while B3 is 500 mm from B2. Also B1 is 50 mm from A. The two parties of beam was aligned by adjusting the spring balance. Then the initial reading from the spring balance is recorded in Table 1 for 0 load column for all B1, B2 and B3 also. Then 5 Newton was applied first at the B1. The spring balance was aligned and the reading was taken. The load B1 was removed and applied at B2. The spring balance was realigned then and the reading was taken. Secondly, the load at P2 was removed and applied at P3. The spring balance was realigned and the reading was taken. Then step 4 to step 9 were repeated using 10 Newton, 15 Newton and 20 Newton for each. Procedure Table 2 Part A. In this time P1, P2 and P3 are fixed at the same location as Part 1. 5 Newton was applied B1 and 20 Newton applied at B3. The spring balance was realigned and the reading was taken. And the part B, P2 is fixed at the same location as before, but B1 is 100 mm and B3 is adjusted to be 400 mm from B2. Then 5 Newton load is applied at B1 and 20 Newton load is applied at B3. Then the spring balance was realigned and the reading was recorded. B2 is fixed at the same location secondly, but B1 is extended to 150 mm and B3 is adjusted to be 300 mm from B2. Then we use 5 Newton load is applied at B1 and 20 Newton load applied is at B3 same time as same before. The spring balance was realigned and the reading was taken. The data recorded can be used to calculate the experimental bending moment. That's all from me. Thanks.
Hello, Assalamualaikum. My name is Nurul Nadra binti Zulkhairi. For the experiment, I will be presenting the result. So, in this result, we have two parts. The first part is the bending moment at different load. So, we set up the distance, which is RA to P1 50 millimeter. P1 to P2 250 mm, P2 to P3 500 mm, and P3 to RB is 100 mm. As you can see in the table, this is the result for part 1 from that we collected from the experiment, and also the theoretical value that has been calculated. So we use 5 different loads, which is 0 Newton, 5 Newton, 10 Newton, 15 Newton and 20 Newton. So each Newton will be added at 3 different points, which is P1, P2 and P3, and this is the balance reading that we get. Okay, from the balance reading that we get from the experimental, we calculate the net force. So to find the net force, we use the value load that we set up, which is 5 Newton, 10 Newton, 15 Newton and 20 Newton. So each load will be minus with the original value load, which is 0 Newton. 0 Newton is 18 Newton. So each of the value load will be minus with the 18 Newton. For example, value load of 5 Newton, which is 19 Newton, will be minus to the 18 Newton, we get 1 Newton. Same goes with the 10 Newton, 15 Newton, and 20 Newton. So after get the net force, we can calculate the bending moment for experimental value. Net force will be multiplied with the 150 millimeter to get the bending moment. For example, in this calculation, the net force of value load 5 Newton, which is 1 Newton, multiplied with the 150 millimeter, we get 150 Newton millimeter. So to find the theoretical value of bending moment at each point, so the first one is at point P1, we'll be using the total moment equal to 0. So we get RA multiplied with the 900, which is its distance, the original distance, minus with the force at P1 that we put, which is 5 Newton, multiplied by the distance of P1. How to get the distance of P1, the original length 900 millimeter will be minus to the 50 millimeter. So we get at 150 millimeter. So and then calculate the value of RA, we get 4.72 Newton. So at moment of so to calculate the moment at P1, when we put the 5 Newton, we put the RA 4.72 multiply with the 300, which is RA to P2, because P2 is the point that we didn't change the distance. So minus 5 Newton and its distance, which is 250, which is 300 that we get, minus with the 50 millimeter of distance P1, so we get 166 Newton millimeter. So the other data in the P1 will be calculated using this calculation. Okay, for theoretical value of bending moment at P2, we also will be using the same formula, which is total moment will be equal to 0. In order to find the RA will be multiplied with the original distance, which is 900, minus 5 Newton, which is the load that we use at the first data at P2, and multiply with the 600, which is the distance of P2, the original length will be multiplied and minus the distance of P2, which is 300, we get 600. 900 minus 300, we get 600, and RA will be 3.33 Newton. So the moment of 5 Newton, which is at the P2, it's just 3.3 multiplied with 300, which is the distance of P2, we get 999 Newton meter. For theoretical value of bending moment at P3, we also use total moment equal to 0, but we take the moment of A, which is we need to find the RB. So RB will be multiplied to the 900, which is the original length, multiply with minus with the 5 Newton, which is the load that we use at the first data at P3, multiply with 800, which is the original length, minus to the uh, P3 distance, which is 100. So 900 minus to 800, we get 800. So RB, we get 4.44 Newton. So to calculate the moment at 5 Newton at P3, 4.44 Newton multiplied with 600, which is the distance between P3 to P2, and then minus 5 Newton multiplied with the 500, which is the distance of P3 to P2, we get 164 Newton meter. As you can see, this is graph of part 1, which is bending moment of each load that we use. So for part 2, we'll be observing the bending moment at different distance. So this is the example distance for the first data. So this is the table 2, which is the data bending moment at different distance. We have, for the first data, P1 will be at 50 mm and P3 will be at 800 mm. Second data, P1 will be at 100 mm and P3 will be at 700 mm. And for the third data, P1 will be at 150 mm and P3 will be at 600 mm. And P2 is constant. For load, each data will be using P1 equal to P1 will be added 5 Newton. There's no load at the P2, and P3 will be added 20 Newton. So each data will be using the same load, so the load is constant. We get balance reading from the experiment, which is 22, 29, and 35. And we calculate the net force, which is the value load of the first data, second data, and the third data will be minus to the original value load, and then we get the net force, which is 4, 11, and 17. After get the net force, we calculate the bending moment in experimental value, which is multiplied with the 150 Newton millimeter at 150 millimeter. So we get for the first data 600 Newton millimeter, second data 1650 Newton millimeter, and the second data we get 2550 Newton millimeter. So we get into the theoretical value. So for the theoretical value of bending moment when P1 at 50 mm and P3 at 800 mm, we'll be using total moment equal to 0, which is 900 RA multiplied by 900 minus to the load that we put. So we put load at the P1 and P3, so we need to minus at P1 and P3. As in part 1, we only put load at 1 point, so we be minus at 1 point only. But in part 2, we put load at 2 different points, so we need to minus at the point that we put the load. So we minus with the P1 and P2 P3. So we get we find the RA, which is equal to 6.94. So to calculate the moment at C, which is the P2, which is the point that we need to find, we multiply the distance of P2 minus to the distance that at P1, which is 50 Newton. We get 2,332 Newton millimeter. Same goes with the second data, when P1 at 100 millimeter and P3 at 700 millimeter, will be using the total moment equal to 0. So the original value RA will be multiplied to the 900, which is the original value, minus to the P1 and its distance, which is 900 minus to the 100, we get 800, minus P3, which is 900 minus 700, we get 200. So RA will be equal to 8.89. So calculate the moment at C, we get 2,167 Newton meter. Same goes with the third data, when P1 equal to 100 millimeter, P2 is equal to 600 millimeter. We'll be using the total moment, which is RA will be multiplied to the original length, which is 900, minus to the P1, 900 minus 150 millimeter, we get 750 millimeter, minus to the P3, which is 600, 900 minus to the 600, we get 300. So RA will be 10.83 Newton. So calculate the total moment at C, which is 10.83 Newton multiplied with the 300, which is the distance at until the C, which is the P2, until the P2, minus minus the P1, because we want the distance only P1 to P2, which is the moment that we need to calculate. So we be minus the P1, we get 2,499 Newton millimeter. So this is the graph for part 2 that we get.
By discussion, which is about the experiment 5 bending moment after the result. In this, we have seen the calculations and the discussion of here. From here is drawn by the bending moment diagram for both the bending moment values getting from the theoretical calculation and experiment value. In this, we have seen here the graph. In here, the graph we have seen here the bending moments, and in here the observation during experimental conducted. The experiment observation during experimental conducted. The experiment is done by determining the relationship between theoretical bending moment and the experimental when the load is being applied load hanger, comparing between the bending moment value obtained from the experiment and the theoretical calculations. In here, we have seen the bending moment value obtained from the experimental and the theoretical calculations. In all of here, the calculations we gotten from the result, which by calculated, and then we have seen here the table, which is bending moment and theoretical value. We go from the table, which was velocity 5 in part 1 and the part 2 and part 3. So for me, that's all about that, the experiment. And thank you very much, all of you.
Hi, I'm Melvin. I will present the conclusion for this experiment. The conclusion for this experiment, we will be able to determine the relationship between experimental and theoretical bending moment when the load is being applied to the load hanger, where the bending moment is directly proportional to the load applied. And we can see this based on the graph plotted from the calculation on part 1. Furthermore, we are also able to study the bending moment varies with the increased load, and bending moment varies at the cut position of the beam for the various loading conditions. where, where when the load is increased, the bending moment also increases. And this we can see from both parts, which is the part 1 and part 2. Lastly, in this experiment, we also needing a precision and care while taking readings, such as we need to make sure that our eyes in a perpendicular position when taking the spring balance uh, when taking measurement on the spring balance scale. And uh, we also make sure that the bubble in the balance located in the uh, also make sure that the bubble is located in the middle before the taking the reading scale. This is because such a small error in the when taking measurement, it will cause us uh, a very different value in the calculation. So I think that's it from